Hello, folks. We are here to talk a little bit more about our module on probability. Last time we discussed some basic lessons of probability, and don't forget the most important one: people are bad at it. Don't be bad at it. And additionally, how to do basic probability calculations. This time we're going to go a little bit farther. We're going to introduce some slightly more advanced probability calculations and talk about how it fits into our process of research. Eventually, we're slowly walking towards connecting this to bigger concepts like the normal curve and z-scores, which are going to come up a little bit farther down the line and make the foundation for those hypothesis tests. So, starting at the beginning, again, we've talked about this a few times, but it bears repeating. It's one of the major challenges of this course. In psychology and in almost any area of research, we are interested in populations, which are the entire set, every single example of the thing of interest, which again usually just means every person you would want to understand. The sample is what we actually get information on. A big part of the course is, again, leveraging information that you get from samples to try to draw conclusions about populations that they come from as accurately as possible. So here's your mandatory candy analogy. So a population might be every single M&M in this bowl. We really want to understand the characteristics of that group of M&Ms, but it's too hard to test all of them. So instead, we just grab a handful, we assess that, and we hope that it's representative of the population. But of course, hoping isn't good enough. You also want to take steps to make sure it's as representative as you can. Anyway, we've seen that sort of stuff before. Here's a new concept in probability, and then we'll stitch them together. So, when calculating probability, sometimes we're interested in the probability of just individual events. Single flips of a coin, a roll of a die, drawing a card out of a deck, all those easy examples of probability. But oftentimes we're looking at the probability of multiple events that take place over time. So things that happen repeatedly. We try to predict the probability of several repeated outcomes, sometimes of exactly the same event, like drawing cards out of the same deck over and over again, sometimes of totally different events that aren't directly related. These events that happen in sequence can be either independent or dependent. So here's how that works. Independent events happen in sequence. One of them happens, then the other, then the next, if you want to keep going. But what happens in those individual events doesn't influence the probability of later events. So, for example, there's a probability that you would attend a class that's held early in the morning. For some of you, that's very high. You make most of your classes your morning people. For others, it's very low. You tend to sleep in, sleep through alarms, more of a night person. But whatever it is, there's some probability you're going to attend AM class. There's also a probability that the temperature at, say, 6 p.m. the same day will be over 80 degrees. Those two things each have a probability, but one of them does not affect the other. Your likelihood of showing up to AM class and whether or not you actually go or not does not change the likelihood that it'll be over 80 degrees that evening. They happen one after the other, but there is no link between them. The probability of the second event does not change based on the first. Dependent events are just the opposite. What happens the first time around, the first event, changes the likelihood of the second event. It alters those probabilities. So, for example, there is a probability that you will attend class, or in this case, view these videos, do the required work. There's some probability, maybe it's very high, maybe it's very low, maybe it's in between. There's also a probability that you will get a good final grade in the course. How that first event turns out, whether you attend class regularly, do the work, how that turns out will shift the probability of the second event. Maybe not as dramatically as we would like it to sometimes, but if you attend class regularly and complete work on time, your odds of getting a good final grade will become higher. If you fail to attend class, your odds of getting a good final grade will become lower. Those events are dependent. What happens in the first event, attending class, alters the likelihood of the second. Now, remember that gambler fallacy that we talked about in the last video? The gambler fallacy actually has to do with taking events that are independent and confusing them, treating them as if they are dependent. The idea of a hot streak, or that I'm due because I'm on a cold streak. People do this reasoning all the time. You may have heard of the old thought example of like a couple has 5 children and all of them are girls. The wife is pregnant again. What's the odds that the next kid is a girl? And the odd is 50%. It's an independent event. It hasn't changed. Just the fact that there's a streak of girls doesn't influence at all the likelihood that the next one will be a girl. So that's the idea. A lot of times the common logical fallacies, we take events that are independent and we think of them or treat them as if they are dependent, as if they are changing each other's probability. Anyway, how do those two things connect together? Well, a lot of times in research is a cycle. When you complete one study, you're going to want to follow up on it and try to get better information. So you're going to be drawing multiple samples, not just from the same population, but oftentimes in the same general pool of participants, like the college students at the same college. This can lead to different what are called sampling strategies that affect the odds of winding up in each of those samples. So here's the first strategy that we can use. We can do what's called sampling with replacement. Sampling with replacement means that we draw a sample from a population, and then before we draw the second sample, they are replaced in that population, which means they are eligible for that second draw. Think of it like this. Think of it as taking a deck of cards. You draw one card at random. The odds of getting that card are 1 in 52. You put the card back in the deck, shuffle it up before you draw a second. The odds of getting that card the second time around or any other is still 1 in 52. What happened the first time, which card you drew, did not influence the odds at all. So the odds of those two events are independent because the sample that was drawn the first time was put back. Think about, again, dumping that handful of M&Ms back in the bowl. Again, shuffling it up. That's kind of gross. Maybe don't do it with your hand. And then drawing a fresh handful. The odds of being in each handful are independent. In real human being research, usually what this means is that if you run multiple studies, participants who go into one study, who participate in one study, who find themselves in that sample, are eligible for the second study. They are put back in the population. They are allowed to participate again. So sampling with replacement creates independent odds. The other approach is sampling without replacement. Let's say that I do not want my first sample to be eligible to be in my second study, my follow-up. Samples are not replaced at all before more samples are taken. This means people or M&Ms or cards that are in your initial sample are ineligible to be drawn into your second sample. This changes their odds. So think about drawing a playing card. Then let's say it's the 6 of spades. Then you shuffle the rest of the deck, but you don't replace it. That 6 of spades stays over to the side. What that now means is that the odds of drawing any other card in the deck have gone up slightly, from 1 in 52 to 1 in 51. There's now only 51 possible outcomes. The odds of drawing that 6 of spades again have dropped to 0 because it is excluded from that population. See how the odds change from 1 in 52 to either 1 in 51 or 0 the second time around? That's what it means to say those odds are dependent. With real human beings, participants who are in your first study are not allowed to participate in your second study. We actually can do this in our research scheduling system. You can make it so that people that participated in one study never even see the follow-up. Why might you do this? If the studies are too similar, they might know your hypotheses, what you're predicting. It could alter their responses. You don't want that. So you might, again, not allow them to be eligible for the follow-up. So again, that's sampling without replacement. That sample, the handful of M&Ms or whatever, is held out. It is withdrawn and is ineligible for future draws. Okay, so here's how we can, whether it's an independent or a dependent event, calculate the probability, what's called the cumulative probability of multiple things happening in a sequence. All that you have to do at its heart is pretty simple. You calculate the probability of the first event you're estimating, calculate the probability of the second event, any other events, however many you've got, and then you just multiply them all together. Keep them in their decimal form. Do not convert them to whole numbers or you'll wind up with some really wacky results. What you should be able to figure out here pretty quickly is that every time we talk about cumulative probability, the probability of those two events consecutively happening is going to be lower than the probability of any one of them is going to happen. The only exception is if the odds of both were either 0 or 100%. But cumulative probability is always lower than individual probabilities, except in those extreme cases. So calculate probability for each event that you're estimating and then multiply them to find the cumulative probability. The only part that gets tricky is you have to account for whether those events are independent or dependent. So when we sample with replacement, our samples go back in the population before the next draw. Probabilities are independent, so you can calculate them separately. The first result doesn't affect the odds of the second. Let's say I'm looking at the odds of flipping a coin twice in a row and it comes up heads both times. Those are independent events. What happens in the first coin flip does not influence the probability of what happens in the second. So in both cases, I have one successful outcome, comes up heads. I have two total outcomes, heads or tails. I get 0.5 for the probability of the first event, 0.5 for the probability of the second, equals 0.25, or a 25% chance that that coin will come up heads twice in a row. It's a little trickier when we sample without replacement. Here, probabilities become dependent. They are changed based on what happens in the first event. So let's take a situation where we start with an equal probability, but we're going to sample without replacement, an equal probability to our coin example. Let's say, again, another classic of probability, we have 5 red dice and 5 blue dice in a bag, 10 total dice. What's the probability of drawing 2 consecutive red dice if you sample without replacement, meaning that first red die gets pulled out of the mix and isn't eligible for the second draw? Well, in the first draw, it looks a lot like the coin example. We have 5 successful outcomes. We have 10 total outcomes. The odds of drawing a red die that first time is 0.5, 50%. The second time, however, we've now excluded that first successful draw. Now there are only 9 total dice in the bag, and only 4 of them are red. So the probability of that would be 4 over 9, or 0.44. When we multiply them, our cumulative probability is now 0.22, or 22%. Notice how we started off with the same probability, but sampling without replacement lowered the odds a little bit, from a 25% chance to a 22% chance, even though we started with exactly the same likelihood. All right, this is our first point of emphasis on basic probability. Calculating probability for individual events usually isn't too tricky. The only thing that people tend to screw up is sometimes they subtract the successful outcomes. They don't count them in the total outcomes. Don't do that. Your successful outcomes are in the denominator as well as in the numerator. Again, keep track of that total number, the number of successful outcomes. It gets a little trickier when dealing with that cumulative probability, consecutive events. This is especially true when those probabilities are dependent. You may have to figure out if probabilities are dependent or not based on how I explain a set of calculations to you. Be prepared to do that. I'm not necessarily going to spell it out. But again, this alters our ability to calculate probability, those cumulative probabilities. And that wraps things up for now. Next time, a really important one, we're going to connect this stuff with our previous material on the normal curve, on z-scores, and we're going to talk about how sample means fit into the mix as well. I'll see you there.